All right, so they seem to think we ought to be able to do this without equations, but if you want to, you can use in section D1. There's no rule against using a section that's not an option that we're using. So in section D1, this is on page 14, right? You can use two equations, and the first one is that the luminosity of a star, which is basically just the power output, is the Stefan-Boltzmann constant times the area of the star times temperature to the fourth, right? So here's your temperature, right? The area of the star, of the surface of the star, is going to be 4 pi r squared, right? And r is this guy. There's your r. There's your temperature. Right? And then just look up the Stefan-Boltzmann constant, right? And that'll give you the luminosity, right? And then the intensity of the radiation is really the brightness of that star, right? Okay, and that is going to be that power output, the luminosity, right, divided by the area of a sphere that has a radius equal to the distance that the planet orbits the sun, right? So that's going to go into your, like that, and then the answer to this goes in there. Don't forget to raise the temperature to the fourth power. It all should be good. This should work. Okay. Then it says calculate the average intensity spread out over the entire surface of the planet. Two things happen, right? The first thing is that the radiation, this thing here, the 2409.9 gets albedoed, right? Okay. So you're going to figure out using this, if you take away 21% of that, how much is left, right? Yeah. So 2409.9 times, right? So you figure out how much is left, and then you take that number, whatever that is, right? And you spread it out over the entire surface of the planet. Remember that it's absorbing pi r squared worth of area frontally from this star, but it's being spread out over the whole planet, right? Right, so they want you to do this times this, right? I would, on an IB test, and certainly on mine, show this ratio. Don't just go, well, I'm going to divide by 4. Why are you dividing by 4? Okay. Calculate the radiative equilibrium temperature, assuming that the atmosphere were transparent to IR. So in other words, if all of it could get loose, right, what would be that radiative equilibrium, right? So you're like, well, what the hell is it? Well, take this answer, right? Okay, take that 476. And it must be radiating at that rate, right? So that's going to be the power radiated by the planet over the area, because intensity is watts per square meter, right? That's watts per square meter. This is watts per square meter, right? And then the power is, of course, emissivity times sigma times area times temperature to the fourth, right? And then we assume, by the way, if they don't give you an emissivity, just assume it's 1, okay? That's the general rule of thumb, unless they've given you like a exhaustive list of emissivities that you're supposed to look up from, okay? Notice that this becomes the Stefan-Boltzmann constant, right? Times temperature to the fourth, right? Is this. So just set that equal. This guy equal to this, right? Take this, divide by that, take the fourth root of it. You should get the right temperature.